Good morning all. So today we are going to discuss the star and delta concept in the three-phase supply system. So let us consider the first star connected system. As we know that if it is a star connected supply system, then the representation of the star connected supply system can be coming as so like this. It has the three coils which are connected in a star connections like this, and has the three lines which has been drawn like this and has been connected to R, Y, B. So this is called a three-phase star connection system, and here we need to identify some the line voltages and phase voltages and line voltages here. So this is the common point. It is also called as the neutral. From the neutral point to that R line, whatever the voltage drop which is appearing here, that voltage drop I can write it is, that is nothing but VRN. And similarly the current flowing through this particular coil, that R phase coil, I can take IRN. So along with the second coil also similar concept you can get here. The voltage induced in the Y phase coil, VYN I'm writing, and the current flowing through this coil is I'm taking as IYN. So is the value I'm going to take. Similarly for the B phase coil, so this is what the current, I can write VBN, and the current is flowing through this one is IBN. So these are the currents and voltages which is flowing through this three winding system here. So here also if you see the voltage, in the line also some current is flowing, that I am assuming that this is the IR current is the line current, and similarly in the Y line the current whatever is flowing, that is IY. Similarly for this B phase, that line whatever the current is flowing, I can take it is the IB is the line currents flowing through this one. And here the voltage in between the R and Y line, the voltage in between the R and Y line, I am assuming that it is VRY, and the voltage between the VY and B line, I am taking VYB, and the voltage in between your R and B line, it is can be assumed as VBR. So these are the some variable I am assigning for this star connected supply system here. So what are these variables we need to understand here. So here I can take what are the phase quantities here and what are the line quantities here. Phase quantities, here the phase quantities are, you can say VRN, and VYN and VBN are the phase voltages. Similarly the phase currents are IRN, IYN and IBN are the phase currents. So because why it is the phase voltages, the voltage from that R line to the voltage from R line in between the R and the neutral point, whatever the voltage induced, that is the phase voltage. Similarly the phase voltage in between the Y line to that common neutral point, that is going to give you the phase voltages. Similarly the whatever the current flowing through these coils IRN, IBN and IYN are called the phase quantities. Now what is that line quantities here? Again we have to define what are the line quantities here. Line quantities you can define here, in between the lines whatever the voltage in between R and Y line, that is VRY is the line voltage. Similarly VYB this is the voltage in between the Y and B line. So VBR is the line voltage in between the R and Y B line. So these are the line voltage you can take. So this is nothing but VRY and VYB and VBR are called as the line quantities. Similarly whatever the currents flowing through the lines, this current and this current are called as a line current, because these are the IR, IY and IB are flowing through flowing through the line, so therefore it is called a line currents. You can define here. So from this star connection, what the observation I made here, it is that whatever the current is flowing in this coil IRN is also equal to IR. So whatever the current IRN flowing through this coil is also equal to the line current IR current. So I can write here my IRN is equal to IR, or I can write IYN is equal to IY, or I can write IBN is equal to IB. So it means that, so these are the phase quantities, phase currents, and these are the line currents, but in case of star connection my phase currents are equal to the line current. So that is the one of the point you need to understand here. Note, in case of star connection the line currents are equal to the phase current. This is the one of the observation we have taken from this diagram. So I can also write I line is also equal to the I phase current. So that is what the one point I observed from this diagram. Now come back to this diagram here. So if you want to write what is VRY, how are you going to write here? So VRY I want to write. So this is nothing but, I am writing here, it is nothing but VRN minus VYN. How I am writing this one? Because if you go back to see the diagram here, I want to write what is this VRY. If you want to write, so this is, you can take it as a closed loop. So this is a closed loop system. If you take, then this voltage plus this voltage plus this voltage, if you write, then that is going to give you the VRY. So I am applying simply a KVL here, the KVL concept. I am applying KVL in that loop, and I am writing VRY equal to VRN minus VYN. So that is minus we are getting, that is because of the polarity direction. So in this loop I am writing VRY is equal to VRN minus VYN. Similarly, if you want to write what is the VYB, what is this VYB, if you want to write, then this is the loop here. So this is the loop here, isn't it? So this is the kind of a closed loop. VYB, this voltage and this voltage, algebraic sum of the this voltage and this voltage is nothing but again equal to 0. So that is what the KVL you can apply here. So I am writing here, it is VYB. How will you write that VYB? So VYB is equal to, I can write VYN minus VBN. So VBN, simply you can, very simple, you can apply a KVL. So similarly, if you want to write what is this VBR, then how will you write what is this VBR? VBR is equal to, you can write what is this VBR is here. I need what is this VBR. So if you observe this one, so this is the closed loop for this VBR. So this is the a closed loop. This is what the closed loop you can see for the VBR. So this voltage plus this voltage plus this voltage drops equal to 0. That is what you have to write here. So if you come here and you write what is VBR here, it is nothing but VBN minus VRN. So these are the relations you can come to know. Or you can say, if it is a vectorial Phasor diagram or Phasor quantities, then you can make it as a Phasor quantities also, something like you can show in a Phasor quantities as well. Now what I am going to try to do here is, so I will draw the Phasor diagram for this star connection. For this star connection I want to draw the Phasor diagram. So to draw this Phasor diagram, what I am trying to do is, first I will take the phase quantities, and as you know, these phase quantities in the star connection, these phase quantities are displaced by a 120 degrees each. So this is what I'm showing here. These are the my VRN, and this is my VBN, VYN, and this is the VBN. I'm going to show here. These are the three phase voltages. VBN, VRN and VYN are the three phase voltages which are displaced by a 120 degrees each, because this is a balanced system we are assuming. Therefore here to here it is 120 degrees, here to here it is 120 degrees, here to here it is 120 degrees. So that is what I'm trying to drawing here. These are nothing but what? This is a phase voltage, isn't it? This is also a phase voltage, VYN. This is also a phase voltage. That is what the given here. Now I want to calculate what is VRY. I want to calculate what is VRY. So it is nothing but what? It is nothing but VRN vector minus VYN vector. If you want to write what is this minus VYN vector, how will you write? What is exactly VYN vector is there? If you shift this vector into exactly 180 degrees, if you shift this vector exactly into 180 degrees, then this is nothing but minus VYN. This is nothing but minus VYN, isn't it? So that is what the 180 degrees exactly, if you draw the oppositely, then it is going to show as a minus VYN. Now what is my VRY here? VRY is nothing but this vector plus this vector. Now what are this VRN vector? This one. This vector and this vector is going to give me, these two is going to give, say, the line voltage. These two are going to give me a line voltage here. So this is what the line voltage we are going to get, VRY. And here you have to understand that what will be the possible angle between these lines here. So obviously you know this is the angle 120 degrees. So 120 degrees it is. So what could be that? This one, this could be a 60 degrees. Then what could be this one? This is a 30 degrees, isn't it? Because each vector is equally dividing the angles, so that you can say it is a 120 degrees, it is 120 degrees, then this is the 60 degrees, but this come to as a your 30 degrees. So this is how the going to show here. What is this VRY? This is nothing but a line voltage. This is a line voltage and this is nothing but your phase voltage. If you observe this one here, and similarly you can draw for the remaining two line also. What is VYB? You can draw this one also. So minus VBN is nothing but coming somewhere here. So it is my minus VBN vector is coming, and if you do this too, so it is going to coming around. This one is nothing but, this is nothing but VYN is coming. Similarly go for the what is VBR. VBR is nothing but minus IRN. So this is exactly opposite direction. You can take minus VRN, and if you combine these two vectors, then this is coming as this is nothing but your VBR vector. So this is how you can draw the line voltages here, line voltages with respect to the phase voltages. So from this diagram, what the concept, what is the my observation I made here is, as we know that your vectors are rotating in anti-clockwise direction. So this is the vector rotation in this anti-clockwise direction. So you can say this is the vector rotation. Vectors always rotates in a anti-clockwise direction. So with respect to this rotation, if you compare the VRY and VRN, it means line voltage and phase voltages here. Then my line voltage, then what is the observation I made here is, my phase voltages are, my phase voltage VRN lags the line voltage, by 30 degrees. So this is another one of the point I noticed from the diagram. Or you can say this is the phase voltage lags the line voltage by 30 degrees. So in case of star connection, phase voltage lags line voltage by 30 degrees. So that is the one another concept we have gone through this one. Now come back here, and if how to understand one more concept here, that parallelogram concept here. So what is this parallelogram concept here? Is nothing but parallelogram concept here. So if you have a vectors, suppose you have the a vector is the a vector and b vector are there. So this is the a vector and b vector is there, and this the summation of these two vectors is nothing but, suppose it is the c vector, summation of the vector, and angle between the a vector and b vector is theta. Assume it is the angle between these two. Then the c vector can be, according to this parallelogram concept, c vector can be written as a square plus b square plus ab cos theta. AB cos theta. This is the one of the concept of parallelogram concept, or under square root of, you can write square into AB cos theta, like that also you can write. So this concept we're going to apply, in this diagram here. So where can you identify that parallelogram here? So this is the one of the parallelogram. This is one of the parallelogram, right? This is, I can take it as a parallelogram concept I can apply here. So this is look like a parallelogram. Then from this I want to write what is this VRY. I want to write what is this VRY in terms of VYN and VRN. So how will you write according to that concept? So you can write here. So this is nothing but VRY is equal to under root of this VRN square plus again the magnitude of VYN square plus the magnitude of VRN and the magnitude of VYN, and cos in between the angle. In between VR and VYN, what is the angle between these two? What is the angle between this vector and this vector? If you see this vector angle, it is this 60 degrees is the angle between these two vectors. So I can write it is a 60 degrees. Or if you see, VRY is nothing but a line voltage, isn't it? It is a line voltage, and this is nothing but VRN is a phase voltage square. This is also a phase voltage square plus this is 2 also the phase voltages. I can write the phase voltage square cos t, this one, this is going to be coming cos theta. So this is also coming as 1 by 2, and I think there is some small mistake we have made here in this formula. It is coming 2ab cos theta, 2ab cos theta. That is what the formula for parallelogram. So with that it is coming 2 VRN VYN cos theta, and here also it will coming 2 values will be going to come. So after this you can these two can be done, and the VL is equal to, if you write this one, it is coming like √3 into V phase. So this is the another relation you can come to know. So what is this relation? So you can observe what the kind of thing you have observed here is in the note. In case of star connection, your line voltage is √3 times of the phase voltage. So this is the another observation we have been made from this diagram. So these are the 3-4 concept you can come to know. So what are the three points you have gone? The first point we noted is line voltage is √3 times of the phase voltage. This is one of the point we made. And one point is your phase voltage lags the line voltage by 30 degrees. That is another point. And another one note is, in case of star connection, your line currents are equal to the phase currents. So these are the 3 points observed from this analysis we have done. Now we'll see that what it could be the power calculations here. What is the power calculations. How will you going to do the power calculations? So as we know that for the per phase or single phase system, if it is, then what is the power calculation? That is nothing but you can say it is Vi cos pi, some kind of equation we know. So you can say it is I phase and V phase and I phase. Similarly, if you want to write for three phase system, then what is the power? It is nothing but 3 times of V phase I phase cos phi, like that also you can write, isn't it? Otherwise you can convert this V phase I phase into line voltages. So 3 in term V phase can be write in terms of line voltages, so you can write in terms of line voltages. So V phase you can write here, it is as root 3 and VL by root 3 into, instead of I phase I can write IL, because in case of star connection the phase currents are and the line currents are both are same. So if you do this one, then P is equal to, we are getting root 3 VL IL cos pi. So this is the another equation you come to know what is that. P is equal to root 3 VL IL. It is called the active power, isn't it? It is active power or a true power. That is what. If you have to write what is reactive power, then this could be coming root 3 into VL IL sin pi. Sin pi will come, that is called the reactive power. If you need what is the apparent power, then it is nothing but under root of P square plus Q square, isn't it? So this is called a apparent power. So these are the concept power triangle. You have already gone through this one, so I'm not going a detail about this one. So this is what the power calculation can be done here. So it is the for three phase circuit, this is power calculation for in terms of phase voltage and phase currents, and this is the power calculation expression in terms of your line voltages and line currents. So this is how you can able to understand the star connection supply system of the three phase AC system. You can have that idea how it can be have the phase voltage and line voltages. Similarly, we're going to see what is the delta connection and delta connection supply system. We're going to see what are the basic connection and how your phase voltages and your line voltage is going to be varying in this case. As we know, so this is the delta connection, means if you have the delta connection, you are familiar with this, how to connect this delta connection, right? So this is what the three windings can be connected in series. So with each one, then is going to form your delta connection. So this is what the star delta transformation technique, where we have already seen how the delta formation can be done here. So they have that R phase and again Y phase and B phase. I'm taking three phases. You have the three coils again. This is R and this is Y, and this is nothing but your B phase, RYB phases. Now again, whatever the voltage drop is there in this winding in between this one, I'm taking this is VRY is the drop, and the current I'm assuming it is IR is the current is flowing through this one. IRY is the current flowing through this one. Similarly, the drop in this winding, I can take the EMF induced, sorry, it is a not a drop, it is a EMF induced in this winding, VBR, and the current is IBR. Similarly, the voltage induced in this coil, this is VYB, and the current is nothing but IYB. I'm going to see here. Now this is the current, is line current IR, you can say. This is the line current IY, and this is the line current in B line, it is that current is IB. Similarly, we can write the voltage in between these two lines, it is nothing but VRY. Similarly, you can write what is the voltage here, VYB, and the voltage between these two lines, you can write here, it is VBR. So like that you can able to define here. Similar quantities also again you can define what are the phase quantities and what are the line quantities. Okay, and the phase quantities are, you can see that what are the phase quantities here. It is VRY, the VYB and VBR are the phase voltages in each line and each windings, and IRY, IYB and IBR are the phase currents. You can write here. Similarly, what are this line quantities? Line quantities you can write here. What are the line quantities we have here? Again, you can go for VRY, again VYB and VBR are the line quantities, and IR, IY and IB are called the line currents. So what is the point, the observation we made from this diagram here? The first observation from this diagram we have made here in case of delta connection is, in case of delta connection, the phase voltages is also equal to the line voltages, because this is the voltage which is appearing across these two lines, R and Y line. So this is the voltage is also equal to this voltage. So that is what the first observation we made from this delta connection here. So I can write in this case the phase voltages equal to the line voltage. So this is what the point I observed from this diagram. So in case of star connection, your phase voltage equal to the line voltage. In case of delta connection, your phase voltage equal to line voltage. In case of star connection, your phase current equal to line current. That is what the observation we made in that case. Now after this, what I am trying to do here is I will take these points. I will take this point. At this point I apply the KCL, because this direction some current is flowing. This is the line current, this is the phase current, and this is also a phase current. So I apply the KCL at the point R. Then what is you can able to find? Apply KCL at R point. Then what is going to get here? It is getting IR equal to IRY and minus IBR. So these are the vector or phasor forms you can able to understand. Similarly, do for this point, and do for this point, and apply the KCL at this each node or junction, and you can able to find the what are these values. So I can write IY is equal to IYB minus IRY. Similarly, if you want IB line current, then this is nothing but IBR, and this is IYB. So these are the different values I am writing here now. So after getting this line voltages, line currents in terms of the phase currents, I will draw the phasor diagram and I will try to find out what could be the possible relations you are able to get here. So to do that one, what I am trying to do again, I will take the this phase currents here. These are the three phase currents I am taking, which are displaced by a 120 degrees each. So I am taking, this is nothing but IRY, and this is my IBR, and this is nothing but IYB. So these are the three phase currents I am considering, which are displaced by a 120 degrees each. Here to here it is 120 degrees, here to here it is 120 degrees, here to here it is 120 degrees displacement is there. Now what I am trying to do here is I want to write what is this line current in terms of this phase currents, this phase current. So I minus IBR is nothing but what? exactly I want to shift this vector into 180 degrees opposite direction. So this is going to define minus IBR. Once you are getting minus IBR here, then what I try to do here, so this is nothing but IRY, this vector, and this vector. If you do these two vectors, then this is going to get me my IR, isn't it? IR. Now if it is, then what is the angle between these two? It is 60 degrees. What is the angle between here? It is 30 degrees. That is what the we need to understand the angle between these two. Now similarly do the same thing for this other also, for the others also. If you do, what could be the relation we are getting here? So this is, I'm going to show here, it is minus IYB. Then if you draw these two ones, then this is going to come me my IB. This is what my IB is coming. Similarly if you do this one, then you can getting this one. So minus IRY, and if you draw these two, so this is going to get my the line current here, that is IY, isn't it? So this is how you can able to understand the phasor diagram of this diagram here. From this phasor diagram, what is the point we are noting here, or we are observed here? It is that, so what is the point we are note or we are observed from this diagram here? It is, and these are the my vector rotation in anticlockwise direction, my rotation of the vectors going in this anticlockwise direction. Then if you compare, this is nothing but what? It is nothing but a you can say it is a line current, isn't it? This is a line current, but it comes to here, it is the phase current. This is nothing but your a phase current. This is the phase current and this is the line current. Therefore what is the point we observed here? It is, in case of in case of this delta connection, my line currents lags phase current by 30 degrees. So this is the point I have understood here. So it is my line current lags the phase current by 30 degrees. So this is the point I observed from this diagram. So that is what I am doing here. So after doing this, what I try to do is, so I will take this part, this portion, I will take this portion now. It is look like a parallelogram concept again, parallelogram concept. You apply that parallelogram concept here, and you try to find what could be the IR here. So what is this IR now? This IR is equal to, you can take it as this IRY square plus this is IBR square plus it is 2 into IRY into this magnitude IBR into cos of angle between these two. What is the angle between these two? It is getting again the 30 degrees, isn't it? This is the 30 degrees angle between these two. You can take it is the 60 degrees, sorry. This is the angle between these two is coming is 60 degrees. I am taking that one. Now after this you can simplify this one. So it is like root 3 into I phase is coming. If you simplify this one, what is this IR? IR is nothing but a line current. So line current is equal to root 3 into I phase current. So this is what the relation we are getting. So you can write the another note here. In case of delta connection, your line currents are equal to root 3 times of the phase currents. So this is the one of the observation we are taking from this analysis. Now after this we'll go for the power calculation. Again the power calculation is same as for the delta connection as well as for the your star connection, because both have the same power calculation. This is for single phase value, this is V phase and I phase and cos pi you are getting. If you want for the 3 phase circuit, it is for the delta connection or star connection, then P is equal to, it is 3 into V phase, I phase and cos pi, isn't it? This is what in terms of phase. Same power can be writing in terms of the line voltages, then it is 3, it is VL, because V phase and VL in delta connection is same, but V phase is equal to line voltage by root 3, isn't it? This is what you are getting for your delta connection. If you do again this one, then you are getting P is equal to root 3 VL IL cos pi. So this is the expression you are getting, right? So if you observe the delta connection and the star connection, so there is a little changes will be there except the power calculation. The power calculation for your star connection and delta connection is same, but when it comes to your line voltages and phase voltages and the line currents and the phase current, there is a difference between those two. So that is the point we need to understand in this concept. So with this I will conclude this session for today, and I hope you understood what is meant by the star supply and what is meant by delta supply, and what are the possible relation between your voltage and currents in terms of phase and the lines.